Okay, the recording is on. The first assignment has to do with the simple example that we are discussing of a mobile robot, a very simplified mobile robot with the planning capabilities, sensory activity, some devices, and so on. Some modules, some subsystems or hardware subsystems, and that's the most important thing, communication issues. Try to develop, even if a bit not completely defined, but just stay inside that, because it will also be the first example used by the ROS course in the lab course, in which I will ask the colleague Karen Recchiuto just to start from this example and to develop the same at a higher level, at the middleware level, that is the ROS system, as I told you yesterday. So keep an eye on this and pay attention to this example. And during the first weeks, we will develop in more details the example. So we can go on with two items. Well, I have to push a little bit and to push you, and because next week we have we don't have the Tuesday class, so I must anticipate some topics of the next week. Let me share the screen. I think that is okay? Can you see the share screen?
Yes, I can.
Okay, okay, thank you. These were the slides that yesterday we were just navigating with some, well, there were some topics to discuss. Let me summarize very quickly. Robot programming and robustness and so on. The example, communication, and we have defined the theory of communication between modules. The term modules is a generic term to include all single algorithm. We will use freely other terms like tasks, like processes or threads or so on. But in general, the module is the typical terminology in ROS. But I think there's no ambiguity, and it is clear what it means. Modules are single processes, single activities interfaced with other modules, exchanging data and running. Typically, they run in cycles, endless cycles. Two categories of communication are message-based and shared memory, and they have a consequence on the programming language primitives. We will see, some of you already knows, but we will develop this. Forms of communication: push, pull, the famous publish subscribe, not available in POSIX, but very common in many infrastructures, also for distributed programming in the network. So it's not strictly related or reduced to robotics. It's not a robotic concept, but it's very widely used in robotics. The publisher subscribe means that a publisher says, I have some data, who wants to know them? And who wants to know them will subscribe and receive data. The important important fact that you will see is that the subscriber receives all data in the sequence the producer generates them. So no data are lost. This implies queues of data because the various subscribers may have different timing in consuming data. Another point is published to a blackboard. It seems simple, but is tricky, so it's not widely used. Sorry, just one moment. Okay. I'm teaching the class. Everything okay. Thank you very much. Bye. Our technician was checking if everything was okay, and I'm not a thief. So, well, so a blackboard is black or white. It doesn't matter. Traditional term is blackboard, but maybe a whiteboard. So in a common board or a sort of manifest advertising thing in which data are posted and everybody, potentially everybody can read data. And in some cases, they are bidirectional, so that there's no difference between producers and consumers, but everybody can produce or consume data. In this case, data can be protected, so giving authorization to consumers and producers and so on and so forth is very complex. So usually they're limited to cases in which it is important to use this mechanism with respect to other mechanisms.
Excuse me, Professor.
Yeah?
Hello, Professor.
Yes, I understand. Speak clearly.
Actually, I ask one question. Yeah. I ask one question. What is driver means?
Driver.
Driver.
Yeah, driver.
Yeah.
Driver. Oh, let me. I can write here.
Range.
Driver. Yeah.
Yeah.
You mean
last? You will get driver from last slide. Go back. Yeah. Here.
driver?
LRF
Yeah.
driver. What do you mean
That's
by
a driver.
LRF driver?
Yeah. Driver, or is a jargon, typical jargon in computer science, and is related to the structure of an operating system. We will start today analyzing roughly the structure of an operating system, and you will see the terminology, in particular the driver, will be cited many times. But roughly speaking, driver is just shortly for device driver. Well, device driver is a piece of software that abstracts the peripheral or the hardware so that you can control the hardware, sending data or making the hardware do something. For example, the device driver for the screen, device driver for a keyboard, device driver for a network interface, or everything is electronic, is pure electronic. So it's a piece of software that activates the hardware, activates and allows the program to communicate with the hardware. For example, when you write to a file, you just send data to the driver of the disk. The driver of the disk accepts standard system calls, system functions that you will see in the next lessons in a standard way, so that there's no difference if you are using one kind of hard disk, traditional hard disk, a solid state hard disk, or something that emulates a hard disk. It's a virtualization of the hardware. So the driver is a absolutely important piece of the low-level part of the operating system. That's the definition of device driver, shortly called driver. Usually drivers are provided directly by the manufacturer of the hardware and included in the operating system, or the operating system manufacturer, producer, gives you an operating system including many drivers for many peripherals. And in many cases, in modern operating system, new drivers can be included in the operating system as soon as you have new hardware whose driver is not already included in the operating system. So you don't have to write a driver. Traditionally, in the real-time course, in the first semester, traditionally, there was an example on how to write a driver, because sometimes a robotician has to write or modify an existing driver. I don't know if also this year this will be in the course. I think it's a very professional, also theoretical knowledge about the professional use of operating systems. So ask the teacher, ask Professor Sgorbissa if this info will be present also this year. Okay, let's go on.
Okay, Professor.
Well, I think I've talked a lot about the driver, but so I will spend less words when the operating system structure will be presented. So we didn't lose our time. So here the topic is communication infrastructure, I think. Okay, communication infrastructure. So to implement the several policies for communication, push, Blackboard, publish, subscribe, and so on, we need some infrastructure. So the operating system or the software you are using needs to support this. Usually, the communication infrastructure is not given directly by the operating system, but is given by the so-called middleware. The most important example that you will see this semester is already mentioned, many times mentioned, ROS. That is an infrastructure as a middleware. Is not the only one. We traditionally in this master course, we teach ROS because it is very useful, clear from teaching point of view, and also easy to understand, and has a lot of it gives you a lot of skills that can be used not only in robotics, in automation in general, and even in distributed software systems, not necessarily with the mechanics and sensors and so on. So, how to send messages? Centralize, where is the pen? Okay, centralize systems, as to say, just do some scratching here. What happens? Okay, a producer 1, producer 2, producer 3 wants to communicate with the consumer 1, consumer 2, directly or not. So directly or Another possibility is just having a central communication system managed by the middleware so that everybody sends and receives messages, sends the subscription issues, requests, sends the request to look to read or write on the blackboard and so on. So this is the concept of centralized central. Everything flows inside a central structure. So the middleware takes into account everything. This is one possible solution. And here there are pros and cons. Better control over message flow. Better control means also security issues. Logging is more simple but and effective. Timestamping logging is timestamp. Timestamp in logging, this is another issue regarding the log files. Timestamp means that every datum written into a log file has also timestamp, knowing exactly the absolute time in which has been produced. So it's one of the keys of having a transparent logging, as I told yesterday. So that is just a log that describes fully how the system behaves, and it makes it possible, for example, to feed a simulation. So the simulation is sort of video clip that is exactly what happened. Another point is dead processes is another problem that in concurrent system very often happens. A process, so a module, a task in general, may die. Usually the death of a process is a catastrophe, is an error in general, but you always have to take into account this. It may die for an error in the logic of the program, may die because some datum acquired from the external is not managed, is not foreseen. So there's no code to process it. So there are many situations in which a process can die. It's very, very difficult in a concurrent system to foresee and to manage all the possible situations. So in general, there are processes dedicated to manage the so-called death of processes. So as much as you can, you write the concurrent program so no unexpected death should occur. But you have also to take into account the fact that in spite of your accuracy, some process could die. And so you have to write a process, or the communication infrastructure does itself, has to manage what happens when a process dies. We will see some examples. In some cases, for safety reason, you stop the whole robot. In some cases, the robot cannot be stopped. If you have a flying robot, you cannot simply shut off the computer, because, of course, the flying robot falls down. So you have to, managing the death of some processes should in any case drive the robot to a safety state, maybe a rest state, shut off state, or maybe a recovery state of some kind. And in any case, the log should report everything. So this is related to the health monitoring. That is a way of deciding if something is going wrong or not. For example, if during messages there are queues of messages that are becoming bigger and bigger and bigger, this means that some process does not consume data, and this probably foresees the death of some process and so on. So centralized communication infrastructure is as good pros. It's clear that probably it is slower. It is slower from the point of view of time efficiency. And this is with respect to, not in, higher network traffic, because everything must go to the same central area. This is an example in which the middleware is aside just to... Yes?
Professor, in the previous slide, right, saying that higher network traffic, right? So if it is a centralized server, means anyway we have an, if for example, if you are installing some application in the centralized server, we have a primary and secondary server, right? So we have one load balancer. We have load balancer to maintain the traffic, right? So how higher network traffic will come into centralized server? Anyway, we are using a load balancer to control the traffic, right?
Load balancer, yeah. You're saying that, yes, there are issues. Load balancer is the correct, it's a higher level issues, but in general is a sort of how to optimize a system in which there is a lot of traffic, of network traffic. Surely you need the balance in the traffic, or that's to say, how to optimize the use of the bandwidth with respect to the wanted communication. And in general, it is easier to do in a decentralized system with no centralized system. In a centralized system, it's very difficult to balance the load because everything goes to the center. And so this is normally a sort of bottleneck. In ROS, there is a centralized system that could be a drawback using the same system for a very wide area system. But in a robot, this is normally a good compromiser between efficiency and simplicity.
Professor, one more question in the previous slide. And I just want to clarify about that health monitoring and higher network traffic. So in case higher network traffic, right? If we receive any high traffic from the centralized server, it will automatically affect that RAM and memory size, everything, right? So health monitoring is also become it will affect health monitoring also, right? Then how are you differentiating that health monitoring is good in the centralized server and the high traffic is impact in that?
This has to say with the giving priority and some rights, superior rights to health monitoring. You will see in the operating system that there's a possibility of writing code which has higher priority, so generally higher rights, and with respect to other processes. And so everything is a monitor, including the processes that manages death of other processes. Everything is critical, like, and has to do with the safety to monitor and to check and so on, will have a higher priority to prevent that the messing in the system affects also the health monitoring or something like that. So the simple solution to this is giving a higher priority, and you will see in the real-time the real-time course the concept of real-time. The real-time concept is the definition of real-time process. You will see is general and includes the fact that the process must respond, must compute before some deadline. A health monitoring is a cyclic process, so as continuous deadlines. And if you define the health monitor like a process with which is hard real time means that in any case it has to compute before the mandatory deadline. You are sure, and you have, of course, the operating system gives you the primitives to define that that process is hard real time. You are sure that everything may happen, but this process in particular always works properly without being becoming slower in computation and so on. So the concept is, just to summarize, you have opened a very important question that we do not address much in this course, and is much addressed in real-time course. How to distinguish computational components like modules, tasks, processes, or threads, how to distinguish with respect to their capability of compute before a deadline expires. That's the definition of real time. Is based on the concept of deadline. A deadline may be soft or hard, and there are a way of deciding how to write a set of processes, of modules in general, so that some of them, not all of them, but some of them are hard real-time compliant. And there is a category of operating systems just that allows you to give the processes this capability. Very, very few operating systems. It depends on the kernel. For example, all this course uses POSIX, the non-real-time part of POSIX, and we use, for example, Linux, which is non-real-time operating system. Nevertheless, it is widely used also in robotics because there are some issues so that you can, in any case, trim process and give higher priority, so they are similar to real-time. Okay. Also in this case, I've talked a lot, but I think that the concept was very important. So I've simply anticipated the concept with respect to what we'll see after. Not so important here, just this topic. Why modules? Well, I think that the answer is trivial. Why modules? Why separate modules? Nodes, the ROS terminology. Each module represents one task: localization, path planning, a driver, probably a higher level driver, not exactly the piece of code inside the operating system. Because in ROS terminology, a driver is also a task that virtualizes a device more than what the simple access to the device provided by the operating system does. Each module runs as a process. What is a process? So we can anticipate. A process is an algorithm, a sequential algorithm. It's a traditional program you write, compile, and execute. Any process thinks of being alone in the world. If a process wants to communicate to another process, is aware that there's another process, and the communication is similar to writing, reading, writing from the keyboard, the screen, a file, and so on. Why we do that instead of writing just one program for the whole robot? Think of the mobile robot with the separate activities like localization, planning, and so on. The answer is some way trivial, like the idea of how I have to write a program with several sub-program functions or objects, different objects, instead of having just one piece of code with everything inside. The fact that modules, in particular in robotics, this is relevant in particular in concurrent programming, in which you don't want to put your eyes and your hands on the whole code, but just on the code that, for example, that computing the localization of the robot, just this one. And you can replace a wrong module or update a module with a new module. So it's very easy to do. Sometimes you can do at runtime without recompiling the whole system. And another issue that the definition of module is the program, so the algorithm, local data, and the communication channels. So a module is something like this with the arrays that are communication primitives that can be publish, subscribe, push, blackboard, everything. We don't mind that. But in any case, once you have defined it completely, just like writing, reading, or communicating to the network. Another point is related to what we said before. You have always to take into account that some module crashes. Dies is a dramatic word, but in general, the other jargon term is to crash. So if this module crashes and this was communicating, you should also take into account that any module should take into account the lost communication, broken communication. So due to the fact that the party crashes. So it's an help in providing the survival of the system or managing crashes. One of the most important module is the graphic user interface. When you write a complex program, you have in any case a graphic user interface, but in robotics it's very, very important and must be completely separated. The main reason is that the graphic user interface for a robot is complex, includes simulation, includes reading log file in case of crash, so analyzing how the system works. So it's a big component. Sometimes the graphic user interface is as big as, well, the robot software itself. So normally, OpenGL is a library for an API for three-dimensional visualization, very common. It's not the only one, but it's so heavy that it usually does not run on the robot, runs outside. A good OpenGL system needs also graphic board, graphic hardware that you do not embed in the robot itself. So the separation of the graphic user interface is typical of robots and in general of many automation systems in which the user interface runs on a completely different machine in the network. Another point is parameters. Well, I have a slide also here. The idea is that parameters are so many because parameters are related not only to the global environment, but also to each modules. So normally a good technique is not to embed in each module the parameters, but to provide a parameter server that is a node itself, is inside the middleware. And so you have one only point where to centralize point in which to trim parameters, a central node. So, but it has no drawback because it is not continuously accessed just at initialization of the initial run, and sometimes when some parameter may change. Some parameter may change also due to some other module. Suppose that the user says, okay, collision avoidance, the AGV, the UAV should navigate 20 centimeters from obstacles. Okay, that's a global parameter, so you put here. And the collision avoidance is the parameter. But sometimes, maybe that you have the sensor interface has detected. You remember that here there is a map of the system, of the environment, including the robot itself, has located some special obstacles or not a moving obstacle, for example, so that an obstacle is moving. In that case, it has to change the parameters that defines the distance, the safety distance for avoiding obstacles, because it is safer to stay more far from moving obstacle with respect to still obstacles. This is a very trivial example, but in general, the parameter server is useful not only because we have only one place in which all parameters stay, but also because some parameters may change during the execution. Well, I think that these were the answers to most of the open views yesterday. I think we can, if there are no questions now, we can rest for 5 minutes and take our coffee and go back. Is it okay for you? There are questions?
Professor, I had one question.
Yeah?
Would we be creating the middleware too, or would that be predefined?
Would be what?
Would we be creating the middleware too, as in would we create the software for the middleware, or would that be given to us?
The middleware, well, the middleware is a concept. as a concept.
Mhm.
In this course, we will not write code related to middleware. We write code at a lower level, just implementing communication and generation of processes and scheduling of processes. And so the low-level communication. The middleware concepts are taught in the ROS course. Is a particular middleware, but it's very has concept very general. So in the middleware, you will see how to generate modules of different kinds, how to establish communication of the communication we have described, and so on, and to make the system work together, including both simulation and real execution. We will show in a sense, how the middleware is implemented. And why we do that? Because in many situations, you don't have the middleware to the upper level. For example, when programming embedded systems that are more and more common in robotics, for small machines or efficient machines. Okay?
Okay. Thank you.
Okay, we stop for 5 minutes, okay? 5-6 minutes. Okay, we are stop share and pause recording. Okay, recording is active. Okay, now we sorry, proceed and we go. We have another topic. Well, first, let me summarize. Since we had today some keyword that we have that was for which I had questions, and so one was device driver. There was another problem regarding the health monitoring in general, or even the load balancer. So the idea of having the task, we call with the general term hierarchy. Hierarchy, how is you write hierarchy?
Yes, it's
Like
correct.
that. Okay, fine. Sorry, I have one crashed neuron. Oh, hierarchy. That's I know exactly the word. Oh, well, device driver. The simplest definition is a piece of the operating system, low-level piece. Very usually it's a piece of code, very short, and just to to manage directly the hardware, and that's the traditional definition. So that when you access a peripheral of any kind, network, motor, sensor, keyboard, anything, you can use a call to the operating system just to carry out the operation that usually is input, output data, or receiving events on the form of interrupts. In the middleware terminology, driver as another meaning that is a generalization of this, is the abstraction by the middleware. A further level of abstraction. So you can, for example, define a driver for the famous laser rangefinder, and you put in your concurrent code of the robot a driver of a virtual machine or virtual sensor that is called rangefinder, so that if you change let me scratch in this way, robot software, I mean, you may use a SICK, I told you yesterday, the most common in industry laser rangefinder, or a simpler system like Okuyo. I don't remember how it is written, maybe this way. This is similar, conceptually similar, as a moving laser, and that gives you back the vector with the distance of all sample points in the environment. They are different machines. They are the same concept. SICK is more accurate, has a range of tens of meters, maybe 50 meters or more. Okuyo generally has a range that is limited to 10 meters or less than 10 meters. The speed of SICK is much higher. The speed, I mean, the number of scans per second, Okuyo is low. So prices are completely different. Levels of security, of safety are completely different. They're different, but you may use one of them. So you write a driver. A driver is a code that is able to manage different peripherals of the same kind, and you write so that you can change the hardware without affecting the code, the main code of the system. So it's similar to device driver. Device driver is at a lower level, so that in any case, when this driver communicates with this one or with this one, it communicates, for example, using USB port or serial line. Serial line, it seems to be, normally we consider serial line communication very old style communication, but it's still in use in industry because it's very robust from the point of view of mechanics, stresses, and electrical noise. But the fact that you are interfacing one of those using this with respect to this is a matter of the device driver. Device driver is embedded in the operating system, and once you connect to one of the line, you have a small piece of code that reads and sends the data. So driver has, just to be correct, two meanings. They have the same meaning in general, but at different level of abstraction. The device driver embedded in the operating system, and the driver you write to abstract in some way and uniform several devices accessed by different device drivers, but in which you have uniformity in managing data. And you do that, or because the middleware gives you a primitive for designing a driver, or you do writing the proper code. The second concept that comes from your questions, and so I think that interaction with you is very, very important, is task hierarchy. Task hierarchy, because the question was, how can I be sure that a certain task, for example, a monitor, never crashes, even if the other processes are crashing or are crowding the system? The answer is giving possibilities of the real-time capability, real-time capability. Real-time capabilities means to have to trim your modules, your tasks, or in general, or not in general, the opposite, in particular processes and threads, give them parameters so that they can respect another color. The key word is deadline. Deadline. A deadline is a time that before that time, your process, your task must compute, must mandatory compute, and that the hard deadline or is hopefully computes before the deadline this is called soft deadlines. Is there a theory of how to schedule, we will see that concept, task in a multitask system so that deadlines are respected or not. And this is a really key point in all hard systems, programming system that drives real mechanical physical systems. ROS, surprisingly, ROS 1, the traditional ROS, is not real time. Real time is a really heavy, important issue, but you know, sometimes it's absolutely necessary. If you have an airplane, tasks inside the airplane that controls the operation of the airplane must in general be hard real time. You cannot miss some deadline. Okay, we can stop the share and go to another. You can go here, I think. Okay. Materials for the Wednesday class. This will be used also in the next week. So I can take directly from here. Or better, I take from here because, no, okay. Okay. This is very simple. Physical robot, control signal, control computer. So in a robot, your software is part of the big universal control loop. Sensor reading and control signals. What is inside the control computer? There is an operating system, just a terminology, kernel. Well, I assume that you know what is a kernel. A kernel is the operating system itself, the always resident in memory. And there is another concept that I assume that you know, that any computer has two two ways of working. One is called user space, and the other is called a reserved or kernel space. What are spaces? Are two modalities of working. Space refers to memory, and in general, the kernel memory is separated as its own addresses. It's separated by the user memory. There are two different spaces. So the kernel has its own memory that is smaller, reserved, and user cannot access the kernel memory. Is unknown for them because the user space, the space in which we load our processes and our memory for our computation, is a space for users. Kernel is a process itself that runs in its own space with privileges that are in particular, kernel can access all user memory or user space and has higher priority. So in any case, at the priority of having the CPU as soon as it is necessary to it. All interrupts, I assume that concept of interrupt is familiar to you, all interrupts jump inside the kernel space. So the kernel space is a machine, is a whole machine. It may be the only one that runs if you don't have user programs. So the kernel, this is the kernel of the system. There are two kinds of kernels, and just to have terminology in general, and this is relevant to robotics and in automation in general. One of the organization is called microkernel, and as the term micro says, is a small kernel, as small as possible. So the kernel has to do in its own space with devices, with all device drivers, memory, and CPU. And that's all. An application is outside the kernel as it runs in user space. So all concept of communication are in the user space because the kernel doesn't care about that. Just running single processes, giving the CPU to single processes, locating the memory, loading into the memory processes, and managing interrupts, and external signals, and that's enough. At the opposite, there is another philosophy that says, no, it's better to have a so-called monolithic kernel. The monolithic kernel is a generalization of the microkernel because the kernel includes also many other functions, in particular, file server, so all input-output, and this is the first time we see the IPC acronym, and we will find it many times, and means inter-process communication. So includes all the support for communication that we have generalized as push, pull, Blackboard, publish, subscribe, and so on and so forth. So communication. And the application asks the kernel a lot of services. In the microkernel, the application can ask the kernel most limited number of services. In that case, all services are managed, many services are managed directly in kernel space. In that case, it's called monolithic because all the components of the kernel, what is managing files, device drivers, the Unix server is a particular case of a server that runs the Unix system calls, the ones that we will describe in this course. Everything. What are the pros and the cons? And this is another way of describing the same thing. Linux kernel, as shown here, is typical monolithic kernel. Is a monolithic kernel, which a lot of things are inside the kernel. Pros and cons. Well, examples. Well, most part of kernels are in reality, most part, we don't have so many kernels. In practice, we have the OS X Mac kernel, we have the Windows kernel, the Linux, Unix, Linux. Linux is just a rewriting of Unix in different way, but at the same philosophy. And we have some other kernels relevant to robotics. I don't know, maybe some of you will use them in your master thesis, for example, like QNX, that is a kernel for strict real time, but there are other real-time kernels. Some of them are monolithic. Linux is Unix, Linux are monolithic. Very few are really microkernel based, like QNX, for example. Here there are some examples. And some kernels are what's called hybrid. Windows 10, for example, is a typical case, which is partially monolithic and partially micro, in the sense that the microkernel is extended with some more activities that in the strict microkernel are excluded. The big difference is that a monolithic kernel usually is more efficient, fast, efficient, and that's the reason why usually Linux runs also on old machines, very slow, with a good efficiency, because it is efficient. Another dramatic cons, not part of the cons, is that you can change something in the kernel only in principle by recompiling the kernel, because you don't have separate modules. There is a technique very often used and used widely in Unix, Linux, and in Windows 2. That is the capability of changing part of the code without recompiling the code and without reloading the full code. OS X, for example, there is a hybrid kernel, hybrid kernel with more issues similar to a microkernel, very often reloads the whole kernel. And so this is the terminology, just to know. Nothing practical in this, but you have to know this distinction. And there is a small example in which we say that the system calls, they are the main topic of our course. System calls are more or less flat, in the sense that Windows, Unix, and of course Linux, they are very similar. So there are system calls, the ones that we will learn to use, because our POSIX system calls have a Windows version that is strictly related. So if you want to port a POSIX concurrent program in Windows, you can change the system calls and with the Windows system calls, or simply use the POSIX subsystem in Windows that is able to comply directly all POSIX system calls. Okay, question about this. So we'll face in just 5 minutes the topic that will be for 2 weeks, and we will start now, anticipate today. That is the anatomy, rough anatomy of the Unix Linux operating system. Okay? To do that, I must find, okay. Okay, let me. No, I'm sorry, I have to do. My, okay. I got one program crashed, so you see that even in a like Linux system, something may crash. Okay. No, I did a mistake. Not this one. Okay. Finally, as I say, can you see the file?
Yes, Professor.
Yes, Professor.
Yes.
Yes, Professor.
Linux basics. Well, in the following, we will use differently Unix, Linux name, it doesn't matter. The contents is introduction to the Unix kernel. As I told you, Unix, Linux for us is the same thing, because from this point of view, there's no difference. We will carry out a rough description of the system with the important concepts. So the differences between the various Unixes and Linux are not relevant for us. We will talk about system calls and interrupts, process management. So finally, we will know what is a process from the point of view of the operating system, and the IPC, inter-process communication, file system, and sockets. Sockets will be the last topic of in our course, and has to do with how is at the low level is implemented communication between processes in the network. Unix is not an operating system, but a family. If you are interested, this is the hierarchical tree of before 93, 93, and should be 91, 93, the years in which Linux was published. Here are some notes on Linux. Linux was born in 1991, 1993. Theoretically 91, but well, a couple of years just to be diffused. Is an completely open source under the contract of the open source contract that is called GNU Linux. In effect, the term the correct term is GNU Linux to emphasize the open source contract. The open source contract means that you can read the code, change the code as you like. You can resell the code in the original way or your modifications and so on and so forth. Normally, the kernel, Linux kernel, we are talking about the Linux kernel. The Linux kernel is distributed freely because you can also sell if you want, but it's not forbidden. But since there are, and if you do some modification of the on the open source code, you can sell at any price your modification, but giving to anyone the possibility of reading the code and to sell himself or herself. So at any price. That's the reason why prices are so low until, from the point of view of the kernel, 0. Linux is distributed, and distributions, or in jargon, distros, the most famous distributions are Debian, Fedora, Ubuntu. There are also some distribution for professional industrial use. It's interesting to know that the most part of the software that supports internet and the clouds, including Windows clouds, as Azure or Azure, are powered by Linux. So, and recently, and since a couple of years, Microsoft has opened the interest in Linux, and there is inside Windows, you may test the Linux subsystem freely distributed with Windows, and there are many parts, and in increasing number of parts of code in Windows that are taken by the open source community, including the new web edge. The OS X is not Unix or Linux, it's different, even if it's very similar, but is POSIX compliant. The kernel is different, so what we'll discuss is not a description of OS X2. There is a mistake. The number of lines of code are estimated as 26 million, so we'll correct. 26 millions of codes. This is a slide important that will be appreciated and discussed at the end, not now. Unit kernel. Last 4 minutes. Kernel, I anticipated, manages the machine's hardware and its peripheral. Is always, almost all in memory. We assume that all the kernel is memory resident. If we have a small system, some part of the kernel may be saved to the disk if there is a disk and loaded when needed. But generally, we can think of the kernel as always memory resident, and provides all services necessary to the processes running through a set of system calls. So the system calls is another point, very, very important. And it handles interrupts. Many system calls refer to interrupts. And we will see the connection between system calls, that seems to be just support to communication, and the hardware. And for us, roboticians, it's very important concept. So I finish now. And we'll see not next Tuesday, but in any case, I will publish all the material before Monday, as usual. Next Tuesday, there will be the Professor Mastro Giovanni meeting about the course in general. We will proceed in any case using the same schedule. So sorry for having reached the end of the time. Goodbye, everybody. Have a nice time.
Bye, Professor.
Bye.
Professor.
Goodbye, Professor.
Thank you, Professor.
You can, as I wrote in the Aula Web, you can contact me by email, or if you prefer, with a push system using the Skype address, so I can receive also on smartphone and answer. Okay?
Sorry, Professor. I have a
Okay,
question.
Bye-bye.
Bye, sir.
Bye.
Bye, sir.
Goodbye, Professor.